So we start. So welcome everyone. So it's a pleasure to introduce Ana Asenjo-Garcia. Ana, she's a physicist. Many of you already know her. So she made her PhD in the Complutense University in Madrid, right? So after the PhD, well, under the supervision of a well-known also physicist here in San Sebastian, Javier García de Abajo, who made his PhD actually here. So she after that, she went to ICFO, as far as I remember. She was also in Caltech after this time. And then she's now in Columbia University in New York for already quite a few years, right? Where she's leading a group in quantum optics. And we are really, really glad to have you here, Ana, once again. And I think it's the first time that you are giving a seminar here?
I think
the second
so,
time?
yeah.
That's the first time. Okay. So thank you very much for coming. And it's a pleasure to have you here.
Of course, thank you so much, Ricardo, for the invitation. I'm going to be here for a week. So if you guys after this talk want to talk to me, I'm pretty much free for any discussion. And so today I'm going to be talking to you about our recent work on Manybody quantum optics. And so I should say that before I, just like ramble on and so on, if you have any question, like please feel free to stop me. I actually enjoy more being stopped and asked than just like talking nonstop. Okay, so let's see if this works. It doesn't work, great. Oh, now I have to leave Zoom. Yes, it works. Okay, now I have to go backwards. Yeah, everything works. Okay, so I guess I shouldn't be saying this to this audience, but we all know that when we have systems where there are many particles interacting, there is emergent physics that appears. And usually, while fascinating, many-body problems are typically hard to understand. And this is because, it's hard to guess principles that describe large systems of particles because these interactions are hard to model. And in principle, this hardness increases with particle number. And so there are situations, on the other hand, that we understand pretty much what happens at a statistical level. And this typically happens when we have systems that are in equilibrium, and precisely because of the theory of statistical mechanics. So an example is we have a system consisting of many spins. We know that if we lower the temperature enough, we will go to a phase where order dominates. And so many-body problems not only appear in situations in equilibrium, but also out of equilibrium. And in particular, when we have systems of particles that are interacting and at the same time are complex, then it is fluctuations and dissipation what gives rise to a spontaneous order. And there are many examples like this that we are familiar with. So one example are lasers, where we have a system that is out of equilibrium, that is driven and that dissipates, yet it emits coherent light. Maybe more, systems that we are more familiar with in our daily life are cities, which are open. They are exchanging information and energy with its surroundings, yet they are highly organized. Another example are chemical reactions with complicated names in Russian. Another example is our body. Okay, so these are situations where you have many particles, they are interacting, but then it's not so obvious to understand the physics because they are usually not, we're not going to think about ground state properties anymore. And so this is the type of problems I care about because I work in quantum optics, and quantum optics problems are by definition open. Okay? And so I should say that particularly in the recent years, there's been a lot of developments in AMO systems where we are building up towards this control complexity. So let me explain what I mean by this. So back in the day, like in the 80s and the 90s, people mostly work with two different platforms. So one platform was clouds of atoms that are disordered. So these are, millions of atoms that are at random positions that are interacting with the many electromagnetic modes of free space. So this is a problem where there is lots of complexity potentially, but it is, hard to control and understand. On the other regime, we have cavity QED. So in this system, we may have one or a few atoms interacting with one electromagnetic mode. And so here it's maybe the other regime where we don't have that much complexity, but we have a lot of control. And in the recent 5 or maybe even now 10 years, experimentalists are able to build atomic arrays. And even before that, optical lattices, where we basically have crystals of atoms. But now, instead of the typical crystal in a solid state system, now the interatomic distances are of the order of microns. So now that we have these platforms, people have really used them to, study many-body physics. And in particular, there are many examples in the literature where people have harnessed Rydberg states to develop basically quantum simulators of Hamiltonian dynamics. So in this situation, most of the work is basically about simulating unitary dynamics, okay? So closed systems, okay? So systems akin to what you typically find in condensed matter. But what I want to talk about today is what does this control complexity mean for quantum optics when we are going to be talking about open systems, because there is, the possibility of emitting a photon, and this photon is going to fly away and we're going to lose energy. And so the first question that comes to mind is, does this matter? Now we have this new platform. Is it any different from anything we've seen before? And the answer is, as always in physics, in the experiments. So these are two recent experiments that I like to explain a little bit about. And these two experiments show that order matters when we have lattices of atoms where the distance between them is of the order of the wavelength of the light that interacts with these atoms. Okay. So the first experiment is one experiment done in the group of Emmanuel Bloch, where they take they use an optical lattice, they form this crystal of atoms, and the interparticle distance is the smaller than the wavelength of the light that comes. Okay, and so what happens when we have light interfacing with this 2D array is that the light gets reflected. And in principle, it can be perfectly reflected. So this basically means that a 2D array of atoms behaves as a perfect mirror. And so in reality, it's not really that perfect. The reflectance is around 70%, but these are, experimental imperfections that people are working on improving. So it's an example of, if you try to do this experiment with a disordered cloud, the light would just be absorbed, and so you won't get any reflection. So this is an example of why order matters, and it matters because of interference. There is a more recent experiment. This year, it's an experiment in a group of Yunye, where they have built a 3D optical lattice for a clock. And what they see is that because of the order, they have very large cooperative lamp shifts, okay, frequency shifts, that appear when the clock is illuminated with light that propagates in certain direction. That makes it basically spatially resonant with some mode in the structure. So between these experiments, there are one very important distinction, that is that this one is truly many-body, okay? So what do I mean by this? In both cases, we have many atoms, but having many atoms doesn't make a problem really many-body. It is having many excitations, okay? So this experiment of the atomic array, in reality, it is just linear optics. There is nothing very sophisticated about it, except for the fact that they can reflect in principle a single photon. But basically here we have one excitation shared among many atoms. And if I want to sound cool, I say atom and quantum mirror. But if I don't want to sound that cool, I can say antennas, okay? So this is physics in reality, where the theory for this is early 20th century, okay? So it's just classical resonators that are collectively reflecting light. They just happen to do that at the single photon level, because these are atoms. Here, the physics is very different. We have many excitations in this array, and that makes the problem complicated, because now we have many interacting atoms. And so if I look at this problem, what I see is the following. This is a many-body problem. I can describe this problem in terms of a spin model with long-range interactions, which also makes it kind of hard. It is open because I have many excitations in my atoms. These atoms can decay, emit the photon, and then I have dissipation. And on top of this, it is also out of equilibrium. Okay, so there is no notion of temperature here. So when I add all of these things up, the solution is that this is a hard problem. Okay, so what can we do to try to understand problems of this nature? Oh, yes.
For the 2D system, is it if I took a atomically thin crystal,
yeah,
like one of those TMD type systems, where there is interaction between excitons,
yeah,
would that come under this class, or would it still be a classical?
No, I think it might.
There is also perfect mirrors that you can realize with the suspended monolayer, for example.
Yeah, I think it's a matter in that case of like the fluence of your laser. So here is the same. So if you start pumping, like more photons into the laser, you're going to have probability of having 2 excitations, 3 excitations, and many excitations. And then the thing is no longer a mirror, it's something more complicated. And so I think that's the same in a solid-state system. So if you manage to create many excitations, then you will have more complicated system, physics. On the other hand, in a solid-state system, you have interactions of other nature, maybe like, like purely like from an electronic origin. And so it makes them also more, perhaps, like interesting or Manybody than just like atoms. Yeah.
Thanks.
Okay, so so the fact that this thing is out of equilibrium and is open and so on means that if I try to go and model this experiment, it's going to be hard. And I need some sort of a starting point, okay, like a problem that perhaps has been solved in history that may guide me. And so this problem is Díez superradiance, okay? So this is, to my knowledge, the first Manybody problem in quantum optics. And it was actually exactly solved in 1954, so many years ago. By Díez. And so let me explain what this is. It's the following. I take a collection of atoms, I put them all in a cavity, and I invert all of them, okay? And so once the atoms are excited, there's going to be basically quantum fluctuations that are going to trigger the emission of a photon. And so once this photon is emitted, it's going to trigger the emission of more, okay? And this is going to yield or give rise to an accelerated emission of light. And what happens is that if you look at the photon emission rate versus time, you will see a burst that scales, or the peak of it scales as n squared. Okay, so this is a situation where we have purely dissipative physics that yields or gives rise to coherence in the dynamics. And so why am I saying that this is a Manybody problem, and why is it easy? And the reason is symmetry. So in principle, this is a problem where I have to consider the exponentially large Hilbert space. I start with all the atoms in a product state, they are all excited, and they start, basically as photons are being emitted, I lower the number of excitations, but I do that instead of exploring the whole Hilbert space in a very specific way because of symmetry. So let me explain. So when I look at what type of state I prepare when I emit a photon, what I'm doing is I'm bringing an atom to the ground state, but I don't know which one. So it can be the first one or the second one or the last one. And when I do that again, then I have 2 holes in my system that I have to, distribute among my atoms. And because of the atoms being in a cavity, they all talk to each other at the same rate, which means that there is permutation symmetry. So of all the very large Hilbert space, the dynamics is constrained to the permutational symmetric subspace. And so the complexity of that Hilbert space actually scales with n instead of exponentially. And so that's why Díez could solve this problem in 1954. And so now what I want to be talking about today is what happens when we don't have so much symmetry to help us. In particular, what happens when we look at these extended systems that are now becoming popular in my community. Does this Díez superradiance exist? And if it does, why and how? Okay. So if you have any questions, now I'm going to be talking about formalism. So it's going to be like a change of pace. No? Okay. So what I'm going to talk about in this talk are three different things. The first one is I'm going to just introduce how to theoretically describe this physics in terms of a spin model. Then I'm going to describe how to find a universal condition that tells me that no matter what type of system I have, I can predict superradiance based on whether this condition is fulfilled. And the last thing I want to discuss is what happens if you were to actually do an experiment. What would you see? And what we predict is that you should see very large shot-to-shot fluctuations and actually some sort of dynamical symmetry break. Okay, so then first of all, I like to talk about what happens with a single atom, and so if I think about a problem of spontaneous emission of a single atom, how does it look like? So I'm a theory, so for me, at least for now, an atom is a two-level system, has a ground state, an excited state, and there is an energy gap of energy h bar omega 0. In general, because of the, this happens at optical frequencies, thermal fluctuations are suppressed. So I have, if my atom is in the ground, at room temperature, most of the population is in the ground state. So now if I take a laser and I flip my atom to the excited state, what is going to happen is that the atom is going to experience vacuum fluctuations, and this is going to trigger its decay. So if I were to do an experiment where I put a detector and I look at the excited state population, I'm going to assume that basically this atom is in the excited state until my detector goes click, and then I know that my atom has decayed to the ground state. And I can describe this in terms of a jump operator that is just simply a sigma minus operator acting in the excited state that brings my atom to the ground state. So now if I were to repeat this experiment, what do I see? I see the following. The click would happen at a different time because photon emission is a process that is stochastic because it's dissipative. And I do it again, and then the detector clicks at another time, and so on and so forth. And then when I average over the many, many decay processes, I get the typical exponential decay of the population that is dominated by a rate that is the spontaneous emission rate that depends on the environment where my atom is. Okay, and I should say that also not only this happens in the time domain, this stochasticity is also represented in the spatial domain, in the sense that if I were to surround my atom with detectors at different positions, each time one different detector would click, and when I average, I would get a dipole pattern. Okay, so now what happens when we have many atoms? When we have many atoms, in principle, this problem is complicated because I have a Hilbert space of dimensions 2 to the n, and I have basically infinite optical modes of free space. So to deal with this complexity, the first thing that one can do is integrate out the photons. And this yields a master equation for the atoms that looks like this. So we have a part of this master equation that is basically describes Hamiltonian evolution. This conserves the number of excitations. And then I have this part, which is the dissipator. This is a Lindblad equation because I have to pay a price for integrating out photons, that is the appearance of this term. And so if you look at this equation, you'll see that this gamma tells me about how atom I talks to atom J. So it does that in a pairwise fashion, okay? So when photons are emitted, they are emitted collectively by all the atoms. And so these gammas are proportional to the imaginary part of the Green's function, which is just the propagator of the field in free space that depends on the positions between atoms I and J. So this is just simply, if I have a dipole and I want to compute the field at some other position, I just multiply my dipole by the Green's function. So this is what you say here. I have, 1D array, 2D array, 3D array, an Eiffel Tower, whatever you want to say. This can be, the environment can be free space, could be a bad cavity, could be a waveguide, etc., etc. So now what I can do is I can take this equation and I can write it in a form that is more comfortable for me. And what I'm going to do is I'm going to take these gamma ij's and I'm going to build a matrix out of this, okay? So this matrix is an n by n matrix that tells me how atom 1 talks to atom 1 to itself, how atom 1 talks to atom 2 to atom 3, and so on. So I can diagonalize this matrix. And when I do that, I find this equation. And so this equation is now written in terms of collective jump operators. So before, when we had one single atom, we had a jump operator that described the emission of a photon. That was a sigma minus operator. Now, when a photon is emitted collectively. So now I have to write a superposition of sigmas acting on different atoms. And the spatial part of that superposition is given by the eigenvector of this matrix. The eigenvalues of the matrix are these decay rates. And these decay rates tell me how likely it is for certain jump operator to act. So for instance, imagine that the decay rate is 0. This means that this decay channel will never be activated, okay? It will be a dark channel. If this decay rate is very large, it means that the atoms really want to emit photons in this mode, okay? And so just to summarize, in principle, I have n of these collective jump operators. And what they describe is the emission of photons with some definite far field profile. And when a photon is emitted, it's going to imprint, this process is going to imprint a set of phases in my atoms, okay? So now, if I want to look at the problem of leaky superradiance, what do I have to do? I have to just take my master equation, and in particular, take my density matrix and use it to compute the rate at which my system emits photons. And so the rate at which I emit photons is minus the rate at which the excitations decrease in the system, okay? And so the number of excitations is just the total excited state population. And I can write this in terms of my jump operators and my decay rates. And so as interactions in principle depend on position, except if I have all the atoms in a cavity or all of the atoms in the same spatial point, I cannot harness this symmetry that I mentioned before in free space and or in a cavity. In free space, this problem is hard to solve. So what do we do about this? So this is second part of my talk. So people have tried to solve the problem of superradiance in extended systems since the 70s and 80s. And eventually, almost all quantum optics theories has encountered this problem. And there is a reason for this because, again, leaky superradiance in some sense is simple because at least there is a toy model case where it has been solved. And it has a very special and simple initial state. So at least there is something in this zoo of possibilities. So there is early work by Haros, Glauber, Everly, Agarwal. There is very beautiful papers, recent papers by Carmichael. And in the context of arrays, there's been a lot of work. Here is a list of papers, each of them associated to some approximation method. So in principle, this problem, as it is hard, you have to try to come up with approximative methods to compute dynamics. And so there are cumulant methods, discrete truncated Wigner approximations, people have used Keldy's and so on. But most of these methods have problems. The first one is that in many cases, these are uncontrolled methods. And sometimes also, and also in most cases, these methods scale poorly with atom number. So even though they are approximate, to get some sort of convergence, you require going to higher orders in approximation, and this also scales poorly. So, you know, there is not that much progress, I would say. And on top of this, it is hard to get an insight on what that drives superradiance, okay? So maybe even if you manage to say, well, if you have a cloud of atoms or a 2D array, you should see a burst, there is no much information that you gain that you can then take and use it to learn about some other problem. So there is another way of going about things, that is try to solve the problem exactly, okay? So brute force. So you can do this. So this is the first thing that we tried. We looked at arrays of different dimensionality. We computed the rate at which they emit photons versus time. And these are our results. These are for interatomic separations that are 1/10 of the resonance wavelength. And so you learn several things from this. The first one is that dimensionality seems to matter. 1D arrays, 2D arrays behave differently. But you also learn that doing this way is very frustrating because we can only look at 16 atoms. 16 atoms is a 4x4 array. If you were to do 5x5, you cannot. If I were to tell you how does this look for a 3D array, I cannot do even 3x3x3 because this is 27. So I don't get any information about scaling or dimensionality from looking at the problem exactly.
Sorry.
Yeah.
What dictates this 16 thing?
This what?
This is 16.
Oh, yeah. So it's basically that the Hilbert space has 2 to the 16, and you actually have to solve a master equation. So you have to solve 4 to the 16 differential equations. And so actually, if you were to solve it via master equation, you probably cannot go beyond 12. So what you do is something called quantum trajectories. So you map the dynamics into the evolution for a pure state, and you do Monte Carlo to basically do all these trajectories that I talked about, like this stochastic process. So yeah, it's basically the complexity is like 2 to the n times the number of Monte Carlo trajectories that you need for it to converge, and that usually scales linearly in system size with some prefactor. So
it's not any basic thing, it's just a computer.
Yeah. So basically you run out of RAM. Like
Sure.
yes. So I don't know how many atoms you can do with 1 terabyte of RAM, but yeah, probably not more than 18. I mean, I don't know, Alejandro, you've tried to do this. Yeah, I think
Exactly.
18 is the more that you can go. So it's like, yeah. Anyway, yeah. So yeah, I think it's the same as if you go and try to solve any kind of many-body problem also in solid state, right? Eventually, like computer cannot deal with it. And so it's like, that's it. Yeah. Anyway. Okay, so then what can you do? You can do things, thankfully. The first thing is I'm a theorist, so I can choose and pick parts of my equation, and I can throw some of them to the trash can, as long as I, fulfill certain things like, probability has to be conserved. I cannot do completely crazy stuff, okay? But within these bounds, I can do a lot. And so the first thing that we try to do is we took our master equation, we took the Hamiltonian, and we threw it to the trash, okay? And this is what comes out. And what you see is that it doesn't matter that much. And so you may say, well, I mean, you're telling me superradiance is a purely dissipative process. Maybe it makes sense that the Hamiltonian doesn't do that much. But historically, when, at least to many people, when you talk about leaky superradiance in these extended systems, the first thing that they are very worried about is this dipole-dipole interaction. So if you look at the Green's function, the real part goes as 1 over r cubed. And so the Hamiltonian, which is proportional to the real part, seems to indicate that basically this 1 over r cubed is going to dominate your dynamics. But actually, thanks to order, this is not the case. So the Hamiltonian doesn't matter that much. So we need to understand this process of the, collective jumps. The second thing that we can do is we can look at the limit where we understand the problem and break it. So we take all the atoms, we put it in exactly the same locations, and then we recover permutational symmetry. This is because all atoms talk to each other at the same rate. So you can exchange atom 1 by atom 2 is the same. And we have a burst. Yay. And then we extend our system. And what we see is that this burst decays. And that makes sense because the interactions in free space depend on the distance, inversely with the distance. So as the atoms are more and more separated, we expect that correlations do not matter and superradiance dies. But another thing we can see is that we can predict whether we can have a burst or not from the derivative of this curve. So it means that this process, in some sense, is a process like synchronization, but it's transient. So either you have the conditions for synchronization to appear, or you have not. So you can look at early dynamics and be able to predict. And this is a huge improvement because instead of looking at the whole dynamics, which involves this like solving for 2D differential equations, you can just look at t equals 0. And you can do this numerically, but you can be a bit more sophisticated and look at it analytically. And to do that, you have to come up with a notion of minimal burst. So what is the minimum burst that can happen is that the first photon accelerates the emission of the second, okay? So if this doesn't happen, you cannot have superradiance. And so the question is, what are the conditions for this? And you can compute this in terms of a second order correlation function that tells you that the probability of emitting 2 photons is larger than the probability of emitting 1 photon squared. If this is larger than 1, you are guaranteed to at least have an epsilon burst. If it is smaller than 1, a burst cannot happen. Okay. And so this involves computing expectation values of a bunch of these jump operators. The expectation value is taken over the initial state, that is all the atoms inverted. And so you do the math, it's like 1 page of algebra, and you find the solution. And the solution is this. So it's very simple. You are going to have a burst if the variance of the set of the decay rates correctly normalized is larger than 1. So what does this mean? So the variance of a set of numbers tells me how different these numbers are among each other. So I want to have numbers that are very different from each other to maximize the variance. I can think now of this process as a process of competition. Now I have atoms that want to emit in different directions, but I want one direction to be dominant. This is what happens in a cavity. I put mirrors. I tell my atoms emit to this optical mode, and this is how there is superradiance. In free space, I cannot tell my atoms, guys, like choose to emit in this direction only, because they want to emit all over the place. But I need to create the conditions for them to do that. And how I do that is by basically putting them all close and by changing the dimensionality of the array. And by relying on constructive and destructive interference. So what this equation tells me also is that it is dissipation what gives me superradiance, but it's also dissipation what takes superradiance away from me. Because if all the atoms emit in the same direction, what this process of emission is doing is reinforcing the phase that the atoms have. So it's like a process of an avalanche that is like being reinforced continuously. If now the atoms emit all over the place, the first photon imprints some phase on the atoms, and the second a completely different phase, and the third a completely different phase, and this leads to dephasing. Okay, so this condition is nice because it gives you this insight, but also it's nice because it means that we can, instead of solving this very large number of equations of motion, we just have to diagonalize an n by n matrix to find whether we can have superradiance or not. And actually, because of the symmetry of this matrix, you can do this in n steps. So we go from 2 to the n to n, which means that now we can look at very large systems and predict things about them. And then one other thing that I should say is that we can take this equation and when we start analyzing systems, we can come up with a notion of critical distance beyond which superradiance is going to disappear. So again, if the atoms are very far away, interference between them and correlations are going to be very faint. We should expect no burst. And as we bring them closer, we should expect this burst to appear. Okay, so just so that you believe me when I say that this is a good figure of merit for superradiance, this is the time of peak emission versus this variance. As soon as the variance is larger than 1, you see that the time of peak emission separates from 0, which means that this peak emission, it is going to happen at a finite time, which means a burst. Okay. So now we look at different systems. And here is what I'm showing you for a 3D array. We're going to look at the critical distance normalized by the wavelength versus atom number. And the critical distance is computed for 2 different geometries. The crosses are numerical results. The lines are basically something obtained semi-analytically. And we see that it grows as a power law with system size. And so everything below this curve, you would expect a burst. and everything above, you would expect monotonic decay in that. So if you were to repeat this plot for a 1D array in 3D vacuum or a 2D array in 3D vacuum, you will see very different behavior. In 2D, the critical distance still scales with system size, but sublogarithmically. And in 1D, it saturates. So you cannot have superradiance, even if you put 10 to the 10 atoms, if the distance between the atoms is larger than 0.3. So this seems to point to some different origin of superradiance that depends on the dimensionality of the system. So this resembles actually what happens in phase transitions, even though this is not a phase transition. So it's a problem that is transient. I cannot talk about phase transitions, but there is a notion of lower critical dimension. So if you think about, the IC model, we know that for 2 dimensions and above, there is, enough neighbors for the spins to sustain long-range order against thermal fluctuations. What we see here is that for 2D arrays in 3D vacuum and above, then there is enough neighbors to sustain long-range order against quantum fluctuations. Quantum fluctuations here means emitting photons in the directions that we don't want. And so in 1D, there is not enough constructive interference. And the only reason why there is any semblance of superradiance in 1D is actually something called subradiance. There are certain states that are actually dark that are activated below certain distance, and basically this modifies this variance to make it large enough. Oh, and the last thing that I should say is that compared to the case of the cavity, where the atoms emit into some optical mode that I'm designing by designing the cavity, here the mode of emission is emergent. So I modify that by changing the geometry of the array, by changing the dimensionality. Okay, so one last thing that I wanted to say about these analytical methods is that I've lost a lot of information by just looking at early dynamics. Okay, I can only tell you whether this system is going to have a burst, but I cannot tell you anything about the nature of this burst. I cannot tell you if you're an experimentalist, oh yes, you're gonna put a detector here and the burst you're going to see is amazing. Okay, this I cannot say. I can only predict if it's going to happen or not. But there are certain ways or certain cases where I can say something else, also in an analytical fashion. I should say that for context, we know that in a cavity, this peak scaling of the burst goes as n squared. So, if you put many atoms, you're going to have a very sizable burst. In free space, this is no longer true. This scaling goes from n to n squared in a non-trivial way that also depends on the interparticle separation. And it approaches n for 1D arrays, and it approaches n squared as you increase the dimensionality. So what can we do? We can actually do something. So what we can do is to invoke something called the Gershgorian circle theorem. Okay. So this is a math slide. So what is the Gershgorian circle theorem? It tells me about the eigenvalues of a matrix and where they lie, basically. So imagine that I have an n by n matrix A. I know that its eigenvalues are going to lie in the union of the n disks in the complex plane defined like this. So what does this mean? I take a matrix, I pick the diagonal element. This is the origin of a center of a disk. I sum all the magnitudes of the row corresponding to this diagonal matrix, and this gives me a radius. And then I draw this disk, and I am guaranteed that in the union of all the disks given by all the rows, the eigenvalues are going to be there. So just as a proof, or as a test, I can take a 4x4 matrix. I can diagonalize it because it's a 4x4 matrix. It's very easy. You'll see the eigenvalues are these red dots. And I can draw circles, 4 of them, because I have 4 rows. And as you can see, the eigenvalues lie in this, in the union of the disks. So what I can do now is to compute this rate is the following. Imagine that I give you a system of atoms, okay? And I tell you pick any state row that you can form, okay? Mix the state with these atoms. And this state may not be reached by the dynamics. It may be some state that you just came up with, okay? That's relevant. For any state, I can compute the photon emission rate because it is just what I told you before, okay? So this expression. I can do a change of basis and I can write it in the local basis as basically this gamma ij sigma plus sigma minus. So if I look at this expression, it looks like a spin Hamiltonian, okay? So I can, for any state rho, I can write the emission rate as the trace of some auxiliary Hamiltonian H. So now the only thing that I have to do to tell you about the peak scaling, it is I'm going to find the largest eigenvalue possible. This is the maximum rate of emission I can have. So finding the maximum eigenvalue of a matrix that is, again, like 2 to the n by 2 to the n matrix, it's hard. But I can bound it using this Gershgorian circle theorem. And this, then the problem becomes how efficient or how good I am at finding tight bounds. And so this Gershgorian circle theorem works very well if your matrix is sparse. And the best case of a sparse matrix is when you have a Hamiltonian that is just nearest neighbor. So this we can prove. If you have nearest neighbor interaction, you give me any array of any dimensionality, then I can tell you that there is no burst. It's impossible. So I can take this idea, and given some bath, I can explore the scaling of the peak. And another example is a 1D array. So 1D array with 1/r interactions, which are basically interactions in free space. Then we can know that the peak intensity cannot scale larger as n log m, which is consistent with numerics. So then you could come take this, any bath, any system, and do the homework of trying to find tight bounds. So at least this we can predict, something about the peak scale. Okay, so with this kind of the more theoretical part of the talk ends. I just wanted to mention very briefly what you would see if you were to do experiments. So just to change a bit of, the experimental setup, we started looking at a more simplified problem that is arrays close to 1D baths. So basically this would be cold atoms close to optical nanofibers or superconducting qubits close to transmission or microwave transmission lines. So in this case, the problem is more simple because you only have 2 jump operators versus n in free space. This is because you can only emit to the left or to the right because of the geometry. You can do the same calculation for 16 qubits. You'll see that you will have a burst. And you can compute the minimal condition, which is pretty much the same, but now normalized to the emission to the waveguide, which is gamma 1D. And you have to overcome some local dissipation that may appear in these systems. So now, if I think about doing this experiment, what would I see? I would see the following. The first photon that I emit or that I detect is going to be randomly detected either to the left or to the right of the fiber because it's spontaneous, it's stochastic. But once the first photon has been emitted, this is going to trigger the emission of many more. So what I'm going to have is some spontaneous breaking of mirror symmetry that is going to be dynamically amplified. So if I were to look for this, what I would do is I would place detectors in the left and on the right of my fiber. And I can compute how many clicks I get from the right, how many clicks I get from the left. I can subtract them. I can call that photon imbalance. And I do this experiment or this numerical experiment many, many times. And what I find is that it is very likely that I get either all photons to the right or all photons to the left. So if you think about what you would get if you had no correlations being built up by the dynamics, it is exponentially improbable to get all of the atom, all of the photons in one direction. But here it is very, very likely. You can design waveguides that are chiral, so it is more likely to emit to the left than it is to the right. And what Superradiance does is it just enhances this chirality. So you are not set by your design, this phenomenon is a phenomenon of avalanche. It amplifies the chirality of the waveguide. And then this imbalance changes with time. So if you now really want to collect all of the photons and you wait for your system for very, very, very long times, what you see is that this probability distribution flattens. And the reason for this is something that I have thrown away before, that is the Hamiltonian. So you can think of leaky superradiance again as an avalanche, but the Hamiltonian eventually is going to scramble your system or your states. So the Hamiltonian plays the role of erasing the memory that dissipation is imprinting in your system. And so just to summarize, what have we learned? I mean, we've learned a bit about this problem. The problem of strongly interacting light matter dynamics is still challenging to deal with, but we hope that these methods of understanding the physics in terms of these collective modes can be applied more broadly, or it may lead to developing toy models where we can capture the physics more efficiently. So I just wanted to mention some of the problems that we're working on right now. So leaky superradiance can be used for developing quantum optics applications, in particular lasers. These are called superradiant lasers. These are not your traditional type of lasers that work via bosonic stimulation of photons that work in these very high Q cavities. Here, these lasers work in the bad cavity limit, where basically the coherence of the process is stored in the atoms and not in the photons in the cavity. So we are very curious to know if we can have lasers without cavities. So we throw the cavity away, we pump the system incoherently. Is there any regime at which we're going to have coherent emission of light? We also know that leaky superradiance generates photon states with metrological properties. And so we're also curious to see if whenever we have extended systems, which are pretty much almost all systems, are these metrological properties going to be preserved? And other thing that we're working on is to try to understand this process in terms of some complexity diagram. We know that the cavity limit, it is simple to deal with. And we know that the arrays in free space, where we have many jump operators and so on, it is very complex. Basically, 1D waveguides are also on the hard side of the problem, but there are certain spacings between the atoms in waveguides where some emergent symmetry properties appear. And we believe that we may be able to go smoothly between easy and hard in this diagram. And hopefully we can use that as a toy model to try to understand better what happens for arrays in free space. And then some other projects involve trying to come up with photon-photon gates using this collective basis that is built from many atoms. We want to understand whether we can have superradiant bursts or use them to probe condensed matter systems. And my dream would be whether we can prepare dark states, which are states that do not decay because of destructive interference, pretty much, via dissipation. And so to try to understand what are the class of achievable states, and perhaps some of them may have metrological and computational advantage. So with this, I want to finish and acknowledge my group in particular, and the people whose names are written are those that participated on these projects, and also our collaborators, Sebastian, Will, and Jacobi, with whom we've been working on knowing whether these physics can be observed in experimental platforms. I'm happy to talk about that if you're interested. And also our collaborators at Caltech and Singapore, with whom we've been working on this Gauss-Coherent circle theorem work. Thank you.
Thank you very much, Anna, for this wonderful talk. So time is open for questions. So let me remind the people that are attending the workshop by Zoom that you can either, well, the best way will be that you write your question in the chat and I will ask the question for you. So, Fernando.
Thanks for a great talk. So the condition for the burst was that the variance of the gammas is larger than 1,
Yeah.
which means that the gammas have to be very different.
Yes, that's correct.
But in the cavity limit, all the gammas are the same.
No, they are different. So it's good that, I mean, it's a good question because it helps me clarify something I didn't say. So these gamma ij's, so basically how atom I talks to atom j, they are all the same. But the gammas that I'm referring to in the variance are the collective gammas. Okay, so and these are the eigenvalues of a matrix that looks 1, 1, 1, 1. And the eigenvalues are, there are n-1 eigenvalues of decay rate 0. So n-1 perfectly dark states, and 1 eigenvalue of value n gamma cavity, if you wish. And so as soon as you have 3 atoms or more, the variance is larger than 1.
So this part in the outlook, when you say mention using superradiance to probe condensed matter systems, do you already have something in mind, or?
Yes, well, this involves my husband. So the idea here is, I mean, in this, what plays a role in this burst, or if you think about this in this like set of decay rates, is not just the arrangement of the atoms, but the nature of your path, right? So this is going to come up as what is the propagator of the electromagnetic field. So then what we were thinking about is, okay, imagine that you have a solid state system or condensed matter system, and there is some phase transition such that you now have some collective modes where, you know, there is that mediate an interaction where the range changes, right? So then you have something that is more local to something that is more extended. And so maybe in some range, this burst cannot happen. And then in this other range, you have a burst. So that's what we were thinking about, but it is all, it's early in the game. But the idea is basically look at some specific condensed matter systems, come up with some sort of propagator, and then maybe place emitters, right? So this is
like the exit on arrays in the.
Yeah, exactly. Yes, that would be part of the. Yeah.
So very nice talk, Anna. In the outlook part where you talk about the cavity-less lasing.
Yeah.
So there is all this. So I just want to understand the role of the cavity is to pick a mode. Am I correct?
It is a bit different. So in the case of like in a regular laser,
Yes.
right? Or at least my understanding of a regular laser, it is the following. You have your inverted system, okay, your whatever molecules, atoms, and so on. And then you have a high Q cavity. And so then the atoms radiate. And what happens is that the cavity is high Q, which means that it's going to store the photons for a long time. So then you start having a buildup of photons in some specific modes. And because of bosonic stimulation, then the atoms know that they want to radiate to that mode. Okay, that's a laser for me. Superradiant laser is a bit different. Superradiant laser, the cavity is a bad cavity. So it has no memory, which means the photons are emitted very rapidly. And it is, at least in my picture of what happens, it is the atoms, the ones that have the memory or what type of photon they emitted. So that's why we were hoping that, so basically the cavity is there to provide an optical mode, okay, but not to build this like large, exactly. So then we were thinking, okay, so now we know that now there are systems like, you know, like 2D arrays of atoms, for instance, where if you place the atom 12, you're going to have superradiance. And so superradiance is basically, in some sense, like you're building correlations or coherence in the atoms. It's just transient. So now I incoherently pump my system. And even though I don't have a cavity, the atoms are going to remember where they emitted, okay, or what type of photon they emitted. And it is believable that there is some pumping rate that can, you know, if you pump super hard, you're going to destroy everything. But there might be a pumping regime where, you know, decay produces correlations, incoherent pumping produces inversion, and so that leads to a laser.
So something like a random laser where,
but it won't be
but a random laser, which is a bad random laser, where you don't want the optical feedback to happen.
Yes. So, but the random, so I think the difference in the case of the random lasing, and this I think is very important with the arrays, and that's why I also wanted to tell you about or talk to you about this like a special material, is that if you were to do this with an dense cloud, right, you have these very large Hamiltonian shifts that are going to quench superradiance and locally phase your atoms. But the fact that you have ordered, this kind of switches off the Hamiltonian. And so then you don't have random lacing anymore. You have ordered lacing, or hopefully. So we are, it's still early in the game, but from what we are able to see, indeed, there is line narrowing and there is G2 of kind of 1, but we cannot do very large system sizes. So this is what we're working on. So hopefully, at least we develop the theory or where you can have, a laser without a cavity. And hopefully there are materials that naturally this appears.
So we have a question from the online audience. So Aurelia Tenu, she's asking whether, hi Anna, very nice talk, thank you. When you define the global observable O in the master equation, it is a sum of Pauli operators that runs from 1 over n. Is it possible to define a sort of cutoff value that defines the range of this observable?
Yeah,
okay.
Sure. So, the range of the observable, it's basically, I guess the question is like, can you define a k-local operator? So it's an operator that doesn't have support over all the atoms. So this is determined by the type of interaction, because these are just like what comes up in the spatial part of the jump operator is just the eigenvector of this matrix that you build from the Green's function. But when we were looking at, for instance, nearest neighbor coupling, this is exactly what we were doing. So now our this gamma matrix is just diagonal and then rows. And so that is going to lead to jump operators, n of them, but they are going to have support only over very few atoms. So in principle, yes, but the question is whether this describes, it's basically the Bath value, which is the appropriate operator. I don't know if that answers the question. Yeah, there are baths like this, like photonic crystals. If you place the emitters in like some sort of photonic crystal and there is a band gap, naturally this type of nearest neighbor interactions appear. So actually Alejandro has a lot of work on along these lines.
The answer of Aurelia is okay, thanks. Any other question? Okay, so if not, I think we can finish the session today. Thank you very much again, Anna, for your
Sebastián,
Si no conoces la última parte, no la había visto. No llegué tarde a tema. Y hablaste de esto.
De waveguide. Y lo del Gerscoring, no, Gerscoring es como una charla.
Lo de que sí, supone
When are you guys
fallar todo lo que
So actually for better, tomorrow anytime. Almost anytime.
I'll probably get here by
casi la posibilidad.
Okay.
Si habría una
I can send you an email, but in principle, there's totally
after 10. Yeah, maybe after 10:30. I will drop the kids off at the camp in the morning.
lo del hotel y la
to send you, I think tomorrow in
si yo hablaría con Adolfo por ponerle la usa la vida y que vengan con los activos del hotel está ese
that's probably better.
además completar el pago por paciente.
Bueno, sí, ahí no te quería preguntar. Sí,
es verdad, porque he dado esta charla y me di cuenta que el teorema no soy capaz de hacerlo.
Es que ni siquiera entiendo el teorema. O sea,
pues que lo enuncias, es muy rápido, y pones la figura, pero si fueras, hay un criterio y estás sosteniendo.
O sea, el tema...
A mí me falta incluso la fórmula matemática, es como que me costaba.
Sí, porque había. Sí, yo también.
Pero básicamente es como cómo hacer un bound del espectro. O sea,
es un bound.
Sí, no, eso lo he entendido.
Y, o sea, es mapeas la parte, toda la parte dinámica
120 de la
a un
noche.
sistema que no hay evolución dinámica.
Y
Y
entonces,
haces
sí,
un bando
sí,
del espectro.
sí,
Y hacer
no gastan, o sea, es
es
hasta,
fácil o
hasta
difícil
eso.
dependiendo de cómo es tu Hamilton.
Porque si no, si dices
En el
según
caso de
la vida y
Disney,
que se lo
pues,
pagamos, igual se van a
Tienes que hacer tus cosas.
María Cristina.
Que sí, cuando puede hablar así.
Ya,
Mañana.
Tiene que ser María Cristina, estupendo, pero no problema.
Vale.
Que sí,
Mañana por la
O sea, el 2, estás tú, el siguiente es el centro de cálculo, es el 3,
Ajá.
y el
Y
que
hay
está al
otro
fondo,
más.
el
Pues
4.
vale, muy bien. No, a
Es
mí
que hoy vamos a ir a comer
Ajá,
con
vale.
Ricardo
Sí,
y
sí.
luego tengo pero mañana
Yo hoy destacar,
después de
¿no?
comer
Es
o
que mañana jueves
O sea, sería-
miércoles, como lo
En el
tiene.
momento que se tuviera
Miércoles por la
la
mañana,
cantidad
después de
toda
comer.
la solicitud y tal, pues pedirlo a, pedírselo a
porque
posteriori.
Es que mañana